Can you hear my voice? Okay. So before starting today's virtual lecture, I just want to tell you that one of the student has asked a question: how many IP addresses and link layer addresses if the router connected to 5 data link layer? So see, this is an assignment question. Okay, I'll show you an example over here. This figure, this figure shows IP addresses and link layer addresses in a small internet. So just go through this and try to find out what will be the possible answer. And the correct answer I'll let you know afterwards. Once your assignment will be submitted, I'll tell you how you can calculate it. But just see this example clearly and just try to make it out how many IP addresses and link layer addresses you want. And one more thing I want to tell you, there's a small correction over here. Now, if you see this, L7, L8, okay, and here you have L1, L2. And if you see this frame, this is L4 and L5, okay. The correction is here, instead of L7, it should be L1, and here it should be L2. Now, why? Because here we have L2, and here we have L1. Like in this case, here we have L4, link layer address 4, so we have used L4 over here, and here we have L5, so we have L5. Likewise, there's a small correction here. It should be L7 instead of L1, and it should be L8 instead of L2. Is it clear? Okay, so make this correction, and in order to why could you repeat? I don't get you. Yes. Yes, Munera. You want me to repeat this again? The reason of changing? Okay. The reason of changing is, yeah. Okay. See here, what we have. Here we have N2, L2. Okay. Here we have N2, L2, and here we have N1, L1. Okay. So instead of L7, it should be L1, and instead of L8, it should be L2. Because if you will see this frame, what you have? You have L4 and L5. Why? Because here you have L4 and here you have L5. Now you have to find it out. Okay, just go through this example and just find out whether it is connected to 4 link layer or how many link layers are there. So if you will see this example clearly, you will be able to answer that question. Okay, Hala? Now, in today's lecture, we will discuss about media access control. As I have told you that our data link layer is divided into 2 sublayers. So the second one was media access control, and the outline of this chapter is, so first of all, we will discuss about random access protocols, then we will discuss about controlled access protocols, and then channelization protocols. So when nodes or stations are connected and use a common link called a multi-point or broadcast link, we need a multiple access protocol to coordinate access to the link. So the problem of controlling the access to the medium is similar to the rules of speaking in an assembly. Yes, Hala. So we should know how many link layer here, and then yes. Go through this figure, okay? Try to find out how many link layers you have over here. So in that case, what will be the IP addresses? You will be able to answer that question if you will go through it, okay, thoroughly. So try to make it out. If still you have problem, then I'll explain it to you, okay? So the procedures guarantee that the right to speak is upheld and ensure that the two people do not speak at the same time and do not interrupt each other, as well as do not monopolize the discussion. So many protocols have been devised to handle access to a shared link, and all of these protocols belong to a sublayer in the data link layer called media access control. So in this figure, you can see that we have categorized them into three groups. The first group is the random access protocols, second group is control access protocols, and third group is channelization protocols. So the first group, that is random access protocol, has four protocols: ALOHA, CSMA. Here there's one mistake. Here we have CSMA also. So we have four categories. We have ALOHA, CSMA, CSMA CD, and CSMA CA. So these protocols are mostly used in LANs and WANs, local area network and wide area network. Now the second is control access protocols. It has three protocols: reservation, polling, and token passing. So some of these protocols are used in LANs, and we will discuss them where the rest of the protocols are used later on. And then we have channelization protocols. It includes FDMA, TDMA, and CDMA. These protocols are used in cellular telephony. Now, this diagram shows you frames in a pure ALOHA network. Before discussing this, let us discuss what do we mean by random access and what do we mean by ALOHA. In random access, no station is superior to another station and none is assigned control over another. So at each instance, a station that has data to send uses a procedure defined by the protocol to make a decision on whether or not to send. So this decision depends on the state of the medium, whether it is idle or busy. Or we can say that each station can transmit when it desires on the condition that it follows the predefined procedure, including testing the state of the medium. So two features give this method its name. First, there is no scheduled time for a station to transmit, and transmission is random among the stations. That is why these methods are called random access. Secondly, no rules specify which station should send next. So stations compete with one another to access the medium. So that is why these methods are called contention methods. So in a random access method, each station has the right to the medium without being controlled by any other station. So if more than one station tries to send, there is an access conflict which we call as collision, and the frames will be either destroyed or modified. So to avoid access conflict or to resolve it when it happens, each station follows a procedure that answers questions like, when can the station access the medium? What can the station do if the medium is busy? How can the station determine the success or failure of the transmission? And what can the station do if there is an access conflict? So the random access methods have evolved from a very interesting protocol which is known as ALOHA, which used a very simple procedure called multiple access. So the method was improved with the addition of a procedure that forces the station to sense the medium before transmitting. This was called carrier sense multiple access. We will study them later on. CSMA, it's there after ALOHA. And this method later evolved into two parallel methods. One is called CSMA-CD, that is carrier sense multiple access with collision detection, which tells the station what to do when a collision is detected. And the second one is CSMA-CA, that is carrier sense multiple access with collision avoidance, which tries to avoid the collision. So we will discuss them one by one in more detail. But first of all, we will discuss ALOHA. So ALOHA is the earliest random access method which was developed at the University of Hawaii in early 1970s. It was designed for radio wireless LAN, but it can be used on any shared medium. So here you can see pure ALOHA network. So the original ALOHA protocol is called pure ALOHA. This is a simple but elegant protocol. The idea is that each station sends a frame. As you can see over here, we have 4 stations. Station 1, Station 2, Station 3 and Station 4 respectively. So each station sends a frame whenever it has a frame to send. So that is multiple access. Since there is only one channel to share, there is the possibility of collision between frames from different stations. So in this figure, it shows an example of frame collisions in pure ALOHA. So there are 4 stations, as you can see, that contend with one another for access to the shared medium, or you can say channel. So the figure shows that each station sends 2 frames, and there are a total of 8 frames on the shared medium. So you have 1, 2, 3, 4, 5, 6, 7, 8. That means total 8 frames are sent. Each station sends 2 frames, so total 8 frames on the shared medium. Some of these frames collide because the multiple frames are in contention for the shared channel. So this figure shows that only 2 frames survive. 1 frame from station 1 and 1 frame from station 3. So we need to mention that even if 1 bit of a frame coexists on the channels with 1 bit from another frame, there is a collision and both will be destroyed. So it is obvious that we need to resend the frames that have been destroyed during transmission. The pure ALOHA protocol relies on the acknowledgement from the receiver. When a station sends a frame, it expects the receiver to send an acknowledgement. So if the acknowledgement does not arrive after a timeout period, the station assumes that the frame or the acknowledgement has been destroyed and it resends the frame. A collision involves 2 or more stations. If all these stations try to resend their frames after the timeout, the frame will collide again. So pure ALOHA dictates that when the timeout period passes, each station waits a random amount of time before resending its frame. So the randomness will help avoid more collisions, and we call this time the back-off time, that is TB, as you can see. TB, back-off time. Now pure ALOHA has a second method to prevent congesting the channel with retransmitting frames. After a maximum of retransmission attempts, that is Kmax, a station must give up and try later. The timeout period is equal to the maximum possible round-trip propagation delay, which is twice the amount of time required to send a frame between the 2 most widely separated stations. As you can see, we have 2 into TP. The back-off time, that is TB, is a random value that normally depends on K, and K is the number of attempts. So the number of attempted unsuccessful transmissions. Now the formula for TB depends on the implementation. As you can see over here, we have a formula. So it depends on the implementation. One common formula is the binary exponential backoff. In this method, for each retransmission, we have a multiplier and it is randomly chosen and it is multiplied by TP. That is the maximum propagation time, or it is TFR. That is the average time required to send out a frame. So in this procedure, the range of the random numbers increases after each collision. So value of Kmax is usually chosen as 15. Now this figure shows the vulnerable time for pure ALOHA protocol. So let us find the vulnerable time, the length of time in which there is a possibility of collision. So we assume that the station sends fixed length frames, which each frame taking TFR. TFR seconds to send, and the vulnerable time for station B. So station B starts to send a frame at time T. Now imagine that the station A has started to send its frame after T minus TFR. So this leads to a collision between the frames from station B to station A. Now suppose that station C starts to send a frame before time T plus TFR. So here there's also a collision between frames from station B and station C. So we see that the vulnerable time during which a collision may occur in pure ALOHA is 2 times the frame transmission time. So we have pure ALOHA vulnerable time is equals to 2 into TFR. Now here we will see frames in a slotted ALOHA network. Now we know that pure ALOHA has a vulnerable time of T into TFR. This is so because there is no rule that defines when the station can send. So a station may send soon after another station has started or just before another station has finished. So slotted ALOHA was invented to improve the efficiency of pure ALOHA. Now in this slotted ALOHA, we divide the time into slots of TFR seconds and force the station to send only at the beginning of the time slot. So this example shows you frames in a slotted ALOHA network. Now because a station is allowed to send only at the beginning of the synchronized time slot, if a station misses this moment, it must wait until the beginning of the next time slot. So you can see we have time slots. These are the time slots. Slot 1 until slot 6. So this means that the station which is started at the beginning of the slot has already finished sending its frame. So there is still the possibility of collision if two stations try to send at the beginning of the same time slot, but the vulnerable time is now reduced to 1/2, which is equal to TFR. Let's see the second figure. Yes, that is TFR. So the vulnerable time of slotted ALOHA is equals to TFR. It is reduced to 1/2. Now we have CSMA, that is Fourier Sense Multiple Access. So to minimize the chance of collision and increase the performance, the CSMA method was developed. The chance of collision can be reduced if a station senses the medium before trying to use it. So CSMA requires that each station first listen to the medium, or we can say that check the state of the medium before sending. So CSMA is based on the principle called sense before transmit or listen before talk. So here CSMA reduces the possibility of collision, but it cannot eliminate it. So the reason for this is a space and time model of the CSMA network we will see, and we'll see that stations are connected to a shared channel, which is generally a dedicated medium, and the possibility of collision still exists because of propagation delay. So when a station sends a frame, it still takes time, although it is very short, but for the first bit to reach every station and for every station to sense it. So a station may sense the medium and find it idle only because the first bit sent by another station has not been received yet. So if we see this diagram, at time interval T1, station B senses the medium and finds it idle. So it sends a frame. Now at time T2, now you see that T2 is greater than T1. So station C senses the medium and find it idle because at this time the first bit from station B have not reached station C. So station C also sends a frame. The two signals collide and both frames are destroyed. Now here we will see the vulnerable time in CSMA. So here it is the propagation time, that is TP. As you can see over here, we have vulnerable time is equals to propagation time, and propagation time is TP. So this is the time needed for a signal to propagate from one end of the medium to another. So when a station sends a frame and any other station tries to send a frame during this time, a collision will result. But if the first bit of the frame reaches the end of the medium, every station will already have heard the bit and will refrain from sending. So figure this 12.8, this figure 12.8, it shows the worst case. The leftmost station, that is A, sends a frame at time T1, which reaches the rightmost station B at time T1 plus TP. So the this area shows the vulnerable time in time and space. Now here we see the behavior of three persistence methods. Now the question is, what should a station do if the channel is busy, and what should a station do if the channel is idle? So three methods have been devised to eliminate this problem. The first one is one persistence method, the non-persistent method, and the p-persistent method. So you can see one persistent method, non-persistent method, and p-persistent method. We will discuss them one by one. So the first one is one persistent. This method is simple and straightforward. In this method, after the station finds the line idle, it sends its frame immediately with probability of 1. So this method has the highest chance of collision because two or more stations may find the line idle and send their frames immediately. Now second one is non-persistent. In non-persistent method, a station that has a frame to send senses the line. If the line is idle, it sends immediately. And if the line is not idle, it waits for random amount of time and then senses the line again. So the non-persistent approach reduces the chances of collision because it is unlikely that two or more stations will wait the same amount of time and retry to send simultaneously. This method reduces the efficiency of the network because the medium remains idle when there may be stations with frames to send. And the third one is p-persistent method. This method is used if the channel has time slots with a slot duration equal to or greater than the maximum propagation time. So the p-persistent approach combines the advantages of the other two strategies. it reduces the chances of collision and it improves efficiency. So in this method, after the station finds the line idle, it follows the steps. Number 1 is, with probability P, the station sends its frame, and when the probability is Q is equals to 1 minus P, the station waits for the beginning of the next time slot and checks the line again. So here you can see. Now here, if the line is idle, it goes to step 1, and if the line is busy, it acts as though a collision has occurred and uses the back-off procedure. Now next is CSMA CD. This method does not specify the procedure following a collision. In this method, a station monitors the medium after it sends a frame to see if the transmission was successful. If it is so, the station is finished. And there is a collision, if there is a collision, the frame is sent again. So in order to understand CSMA-CD, let us first see the first bits that are being transmitted by the two stations which are involved in collision. So let's see this figure. Now, although each station continues to send bits in the frame until it detects collision, we show that what happens as the first bit collide. Now, in this figure, station A and C are involved in collision. Station A and C. Now, at time t1, station A has executed its persistence procedure and it starts sending the bits of its frame. And now at time t2, the station C has not yet sent the first bit sent by station A. So station C executes its persistence procedure and it starts sending the bits in its frame, which propagate both to the left and to the right. The collision occurs sometime after time t2. So station C detects a collision at time t3 when it receives the first bit of A's frame. Now station C immediately or after a short time aborts transmission. It aborts transmission. Now station A detects collision at time t4. When it receives the first bit of C's frame, it also immediately aborts transmission. Now we see that A transmits for the duration T4 minus T1. This is the transmission time, T4 minus T1. And C transmits for the duration of T3 minus T2. Now for CSMA CD to work, we need a restriction on the frame size. So before sending the last bit of the frame, the sending station must detect a collision and abort the transmission. This is so because the station, once the entire frame is sent, does not keep a copy of the frame and does not monitor the line for collision detection. Therefore, the frame transmission time, that is TFR, must be at least 2 times the maximum propagation time TP. So let us think about the worst case scenario, that if the two stations involved in a collision are the maximum distance apart, the signal from the first takes time TP to reach the second, and the effect of collision takes another time TP to reach the first. So the requirement is that the first station must still be transmitting after 2 TP. Now look at the flow diagram for CSMA CD. It is similar to the one for the ALOHA protocol, but there are some differences. The first difference is the addition of the persistence process. So we need to sense the channel before we start sending the frame by using one of the persistence processes we have discussed just now, that is non-persistent, one persistent or p-persistence. And the corresponding box can be replaced by one of the persistence processes. The second difference is the frame transmission. In ALOHA, we first transmit the entire frame and then wait for an acknowledgement. In CSMA CD, transmission and collision detection are continuous processes. So we do not send the entire frame and then look for a collision. The station transmits and receives continuously and simultaneously using 2 different ports or a bidirectional port. So we use a loop to show that transmission is a continuous process, and we constantly monitor in order to detect one of the 2 conditions. Either transmission is finished or a collision is detected. So either event stops transmission. So when we come out of the loop, if a collision has not been detected, it means that the transmission is complete and the entire frame is transmitted. Otherwise, a collision has occurred. And the third difference is the sending of short jamming signal to make sure that all other stations become aware of collision. This one. This figure shows the energy level, which is during transmission and idleness or collision. So we can say that the level of energy in a channel can have 3 values. Either it can be 0, or it can be normal, or it can be abnormal. So at the 0 level, the channel is idle. At the normal level, a channel or a station has successfully captured the channel and sending its frame. And at the abnormal level, there is a collision and the level of energy is twice the normal level. So a station that has a frame to send or is sending a frame needs to monitor the energy levels to determine if the channel is idle, busy, or in collision mode. Next we have CSMA-CA. It was invented for wireless networks. Here collisions are avoided through the use of CSMA-CA. Now see this flow diagram of CSMA CA. So first, collisions are avoided by differing transmission even if the channel is found idle. When an idle channel is found, the station does not send immediately. It waits for a period of time called the interframe space or IFS. Even though the channel may appear idle when it is sensed, a distant station may have already started transmitting. So the distant station signal has not yet reached this station. The IFS time allows the front of the transmitted signal by the distant station to reach this station. And after waiting an IFS time, if the channel is still idle, the station can send, but it still needs to wait a time equal to the contention window. So the IFS variable can also be used to prioritize stations or frame types. For example, a station that is assigned a shorter IFS has higher priority. This diagram shows contention window. Contention window is an amount of time which is divided into slots. So a station that is ready to send chooses a random number of slots as its wait time. The number of slots in the window changes according to the binary exponential backoff strategy. This means that it is set to one slot the first time and then doubles each time the station cannot detect an idle channel after the IFS time. So this is similar to p-persistent method, except that a random outcome defines the number of slots taken by the waiting station. This diagram shows you CSMA CA. This is a mistake. It should be CSMA CA. CSMA CA. Slash CA and NAV. NAV stands for Network Allocation Vector. Network Allocation Vector. So when a station sends an RTS frame, as you can see, it includes the duration of time that it needs to occupy the channel. The stations that are affected by this transmission create a timer which is known as Network Allocation Vector, that is NAV, that shows how much time must pass before these stations are allowed to check the channel for idleness. So each time a station accesses the system and sends an RTS frame, other stations start their NAV. So in other words, each station before sending the physical medium to see if it is idle first checks its NAV to see if it has expired. Next we have controlled access. Here the stations consult one another to find which station has the right to send. A station cannot send unless it has been authorized by other stations. So in this, the first is reservation. In reservation method, a station needs to make a reservation before sending the data. So if there are n stations in the system, there are exactly n reservation mini slots in the reservation frame, and each mini slot belongs to a station. So when a station needs to send a data frame, it makes a reservation in its own mini slot. The stations that have made reservations can send their data frames after the reservation frame. As you can see over here, it shows a situation with 5 stations and a 5 mini slot reservation frame. In the first interval, only stations 1, 3 and 4 have made reservations. In the second interval, only station 1 has made reservation. Now next is polling. Polling works with topologies in which one device is designated as a primary station and the other device is the secondary station. Now here, the select function is used whenever the primary device has something to send. Now the primary controls the link. If the primary is neither sending nor receiving data, it knows the link is available. If it has something to send, the primary device sends it. The poll function is used by the primary device to solicit transmission from the secondary devices. When the primary is ready to receive data, it must ask for poll. And each device in turn, if it has anything to send, when the first secondary is approached, it responds either with a neck frame if it has nothing to send, or with data in the form of data frames. If the response is negative, a next frame, then the primary polls the next secondary in the same manner until it finds one with data to send. So when the response is positive, that is, a data frame is being sent, the primary reads the frame and returns an acknowledgement, that is ACK, verifying its recipient. Then we have token passing. So in token passing method, the stations in a network are organized in a logical ring. You can see this figure. Here we have physical ring, dual ring, bus ring and star ring. So in the physical ring topology, when a station sends the token to its successor, the token cannot be seen by other stations. The successor is the next one in line. So this means that the token does not have to have the address of the next successor. Now the problem with this topology is that if one of the links, the medium between two adjacent stations, fails, the whole system fails. Now second is dual ring. In dual ring topology, it uses a second ring which operates in the reverse direction compared with the main ring. So the second ring is for emergencies only. Now next is bus ring. In bus ring topology, this is also called token bus. the stations are connected to a single cable which is called bus. So it makes a logical ring because each station knows the address of its successor. Yes, dual ring? Yeah. In this dual ring topology, it uses another ring, okay, dual ring. So one is the original ring and second one is the auxiliary ring, and which operates in the reverse direction. As you can see over here, the arrows are reversed. The arrows are reversed. So it operates in the reverse direction compared to the main ring. Now the second ring is for emergencies only. So if one of the ring in the main ring fails, the system automatically combines the two rings to form a temporary ring. And after the failed link is restored, the auxiliary ring becomes idle again. Now in last one we have a star ring. In a star ring topology, the physical topology is a star. We have a hub, as you can see. We have a hub in between that acts as a connector. The wiring inside the hub makes the ring. The stations are connected to this ring through the two wire connections. This topology makes the network less prone to failure because if the link goes down, it will be bypassed by the hub and the rest of the station can operate. And lastly, we have channelization. So channelization, or we can say channel partition. It is a multiple access method in which the available bandwidth of a link is shared in time. Now here we have three methods. We have FDMA, we have TDMA, and we have CDMA. So FDMA is frequency division multiple access, where the available bandwidth is divided into frequency bands. As you can see in this figure, FDMA specifies a predetermined frequency band for the entire period of communication. This means that stream data, a continuous flow of data that may not be penalized, can easily be used with FDMA. So we need to emphasize that although FDMA and frequency division multiple access conceptually seem similar, there are differences between them. So we'll discuss them later on, what will be the differences. Then we have time division multiple access, where the stations share the bandwidth of the channel in time. Let's see this figure. Yes. Here in TDMA, the bandwidth is just one channel, that is time shared between different stations. And then finally we have CDMA, that is code division multiple access, and it was conceived several decades ago. So CDMA differs from FDMA in that only one channel occupies the entire bandwidth of the link. And it differs from TDMA in the sense that all stations can send the data simultaneously and there is no time sharing. So this was all about media access control, and go through this chapter. If you have any doubt, any problem, you can mail me, or in my next face-to-face lecture, if you have any doubt, we will discuss it again. See you next week. Till then, take care all of you. Assalamu alaikum.